Good morning. Welcome to Krishna's classroom. In this talk, we explore a fundamental theorem of mathematics, namely the fixed point theorem. Well, there are hundreds of versions of fixed point theorem which emerge, but the basic result appeared way back in 1910 and 1911, and it was Hadamard who gave a initial version of it, and later it was more generalized by Prover. The theorem stated in the following: every continuous self-mapping of the closed unit ball in a Euclidean space, fixed point. This means if B is if F is a map from B, where B is the closed unit ball in a Euclidean space, to B, it's a self-mapping, then there exists X belonging to B f of X equal to X. That is what we mean by self-mapping. That is what we mean by it is a fixed point. Now X is called a fixed point of in fact, it is turned out to be a fundamental theorem of topology with far-reaching applications in the form of applications to prove the existence of solutions of differential equations and problems in the area of differential geometry. So it had applications to prove existence theorems. In fact, this whole problem became sensational when a fascinating popular article appeared in Scientific American in the year 1966. So the January edition, January 6. I think the volume was 214, I believe. Yes. 214 by Marvin Shinbrod. Now the theme of this article was, of course, fixed point theorems, and presented in a very popular language so that it is accessible to not only professional mathematicians but to the scientific community at large, and even people who are not who are probably not scientists. Now this article evinced a lot of interest, and that was a time when so many articles started appearing on this topic, namely the so-called fixed point theorems. In various circumstances, it became almost a publishing industry. And even now you can see in our country there are research theses or PhD theses written on fixed point theorems in some context or other. It turned out to be one of the fundamental theorems of topology, as I mentioned it earlier. Now, the way or the language in which it was presented by Marvin Shinbrod was very fascinating. He presented it as a coffee stirring problem. This is interesting. Now it says the following: no matter how the surface of the coffee in a cup is continuously deformed by gentle stirring, there will always be a point on the surface in the position it occupied at the start. So what it means is you have a cup in which coffee is there. Now you use a spoon to stir it up, but not very violently and very gently, so that the points on the surface do not go inside. I mean, this is, I don't know whether it is ever possible or not, but certainly, at least for stating this result, we assume that it is possible. That's why it is this word gentle stirring is made use of, that you don't do anything violent in the process of stirring, so that the points just go inside. Okay. Then what it says is that there is always a point. Okay, you stir it and leave it there, settles down. Then what happens? There is a point which occupies the same position as it did in the start. It's not the same always. Now, if you further stir it, there may be some other point which has this particular privilege. And this is the so-called coffee stirring problem. Or in short, what you say is that if you consider the consequence of coffee stirring as defining a map from the surface to itself, continuous with the property of continuity, then it says that there is always some point on the surface in the position it occupied at the start. Now that's a very popular version of it. It's about a 7-page article which is fascinating, and there are a lot of different things discussed there. Now, what we explore in this lecture is the so-called Banach's contraction mapping principle, and what it says for the so-called fixed point theorems in a very general setting like a metric space. Okay, but before that, let us look at a simple problem. And then appreciate what goes on. Now you see that you are now looking at a map from on the real line, which maps the interval 0, 1 to 0. The closed bounded interval. Now we will slowly look at the problem and start investigating certain things with this example. Now you see that we assume f is continuous. So we can draw the graph of this function, and what it says is this following. This is the interval 0, 1. Now in this frame, the graph would stay in this square, and the function would be, if you are mapping from the interval 0, 1 to 0, 1, then the image would be here. So the graph would be taking some form of this kind, so that you are assured that the graph is x f of x belongs to the this is assured. Now, what do we mean by it has a fixed point? So, we are looking at this problem fx equal to x. So, we have got two functions y equal to fx and y equal to x. Okay, and we are looking at the intersection, possible intersection of these two curves. Y equal to x is the following curve, namely the diagonal of this rectangle. Now you see that certainly there exists some point x lying on the domain where fx equal to, so this is a point. This is the point x fx or fx equal to. Similarly, there are other points here, the way in which we have drawn it. There are other points here which have the same property. So, obviously, you can have continuous functions defined from 0, 1 to 0, 1 having more than one fixed points. That's clear. So, under the assumption of f is continuous. Now, let us explore this problem with this example further. Okay. First of all, we observe that there always exists. There always exists a fixed point. Why is it so? It's because of the following. We can give a very quick proof of this. It's obvious also, because suppose you have a there exists no such fixed point, which means the graph of f does not cross the diagonal. Okay. There does not exist a fixed point. The graph of f does not cross the diagonal of 0. In such a case, what happens? See, this graph cannot cover here. That means the function will not be. In such a case, f is not defined on entire. That is obvious, because suppose the graph lies only here. Suppose the graph lies only here. Then what happens? You see that this won't be defined on the entire. So this will be the domain, and you can make it further down, unless you include this point also, because you are defining from here to here, and you cannot cross this and go across. Okay, therefore, in that case, f is not defined on the entire 0 point. Okay, because we are talking about a continuous function. So if it is, the graph is somewhere here, this is the same story. You will have problems on this side. Maybe defined here, but would have problems on this side, because you cannot include this point. You include this point, then you are defining on the whole domain. Because if both these points are included, then certainly this is some fixed point, or at least one of these points are included on the, or lie on the graph of it. There is a fixed point, so it cannot be. Okay. So if such functions cannot have either this endpoint 0, 0 or 1, 1 lying on it. Okay. So in that case, the function is not defined on the entire 0, 1. So that is against the definition of the function. Okay. Now you see that from the graph of the function we have drawn, it's already clear that there could be more than one fixed point. Drawn, it is clear that there could be more than one fixed point. It is the set of all x which gets mapped into itself, and that is the point that is obtained by looking at what is called the intersection of the graph of the function with the diagonal. So from there you can figure out the fixed point. That means this graph could be crossing over this diagonal more than once. But if it doesn't touch the diagonal at all, then you may not have what is called the function defined on the whole interval. Okay. But how do we actually give a mathematical proof of this? This is quite easy. Look at the function. Fx minus x. So g is defined from 0 to 2. Okay, right? So g is defined from 0 to 2 and g is continuous. Sorry, 0, 1, 2 and g is continuous. This is actually an into map. So it's a continuous function. Now, what one observes is the following. Suppose G0 equal to 0. Then we have F0 equal to 0 and consequently zero is a fixed point. Now suppose G1 equal to 1. G1 equal to 1, which implies F1 minus 1 equal to 1. Sorry, think. What is it? Suppose G1 equal to 0. Equal to 0. Then we have F1 minus 1 equal to 0, which implies F1 equal to 1. Okay. Therefore, that is 1 is a fixed point. Now what one does is this: assume these are the two different cases that we have looked at. The third possibility is that neither G0 equal to 0 nor G1 equal to 1. Nor G1 equal to 0. Suppose both these cases are not there. Then what happens? If G0 is 0, see from the graph, I'll draw the graph again. So the situation is this. Suppose this is y equal to f of x. That is the graph of. Now you see that at G0 is not equal to 0, G1 is also not equal to 0. What is the consequence of that? See, since zero one, clearly G0 is what? G0 is F0 minus 0, so that is positive. Similarly, G1 is actually 1 and F1 is less than 1. Therefore, so G is a continuous function. So G is a continuous function defined on the interval 0, 1 such that G0 is positive and negative, which implies there exists some x belonging to 0, 1 such that G0 equal to Gx equal to 0. What does it mean? That is f of x minus x equal to 0 or x is a fixed point of f. So there exists a fixed point for, so we have given a very elementary using basic calculus. We have essentially shown that there is a fixed point for the function f. Okay. Now what if we delete what happens? One say if or even 0 1. Okay. Then it is easily seen that one could construct a continuous function on no fixed point. That is, we are talking about a continuous function defined from one could construct a function which is not continuous. Okay. For example, you can have a graph of this, a function like this, now taking the interval like this, and range like this, and then we are trying to fix a graph which does not cross this. So something starts here, say, then possibly tends towards this. But since this point is this, so here we take the case where goes to 1 as 1. But fx is greater than x. Similarly, you can construct on the below also the same kind of. So there you will be talking about functions of this kind. So you see that this is the scenario that you have. Therefore, one observes that if you drop closed boundedness or even closeness, because we are talking about a bounded interval, then the problem becomes difficult. In the same way, if you were to consider a f from infinity continuous, then one could have a function f constructed from 0 infinity to 0 infinity which has no fixed point. That is possible. no fixed point. So that gives some incisive information about the type of maps that you have, or the domain and the range will have to be the same. Also, if you change the range, of course, it is needless to say. It's needless to say that if the range is different, then there exists functions f with no fixed point. Even this question may not make any sense. Okay. So what we need is that the domain should be bounded. It should be a closed domain. So the same arguments can be repeated for continuous functions from a compact interval to a compact. In fact, it is shown that in a Euclidean space, more generally, the Euclidean space, if f is a continuous function, okay, so what we have shown in the beginning, or what we have written in the beginning, is that if x is a space and f is a map from B where B is a closed unit sphere, then and if f is continuous, then it has a fixed point. So this is the generalization that you. Now, one of the questions that we take up in this talk is, as we have seen from the example, that the fixed point may not be unique. So we asked the following question: what further condition on the map assures F has a unique fixed point. Now, it is interesting, it is of interest for the following reason. See, why it is of interest? Because there are many equations that we come across where we would like to find out whether there is a unique fixed point or unique solution for the equation. The problem is this: why you talk about unique fixed point? I'll just give an example. I am not making anything or specific about the domain or anything. We would rework. Suppose you have a function f from some x to x. Okay, and we assume f is continuous. I have not put any restriction on x yet. So it's some matrix space or something. Now suppose you have a problem like this. Want to find out given y we would ask as a solution this is the first question. Is such a solution unique? Now, how do we repose this problem as a fixed point one? What we do is we define a new function f(x plus x). So we look at the following problem. X minus y. Now we would like the following. Suppose G has a fixed point psi. Then what do you have? We have psi. G psi equal to psi. What does this mean? This means the following. This means the following, namely, so G psi equal to F psi y. Okay. And what we have is G psi equal to implies F psi plus psi minus y equal to psi. That is f of minus y equal to 0. So if psi is a fixed point of G, then it is a solution of the given equation. Hence, if is a fixed point of G, then it is a solution of the given equation. Okay, so such problems can be recast in the language of a fixed point problem. Therefore, the moral of the story is this, that hence equations the problem of finding solutions of equations can be reposed as finding the fixed point of finding the fixed points of I have assumed that all these addition and subtraction etc. makes sense. I have assumed x is in this case. So in some situations, it is possible to rework the whole problem in the language of and transform it into seeking the fixed point of a map. That's the relevance of this particular question. Now the question that we raised is that Okay, we have somehow we can prove that there exists a solution for the given problem. Now, is this unique? Quite often, unique solutions are of importance in the study of different types of equations. You would ask the normal question to ask whether the solution, a solution that exists, is uniquely determined or not. And so in the context of differential equations or integral equations and so on. Now later we will be doing some examples also where the modus operandi will be clear. And this is only a sort of holistic computations which give some idea. I have assumed it is a linear space because all these adding, subtracting, all these things should make sense. Okay. Now let us, in this context, just found that you need additional conditions, as it is clear from our exploration. Certainly you need some further conditions than continuity to assure that there is uniqueness. And this is assured by assuming that the map is what is called a contraction. What is it? I mean, I'll give a feeling for the whole problem in a different way. You are all familiar with the frames, that's wooden frames or metallic frames that you use to keep the clothes stretched while doing some crochet stitching on the clothes. So it's something like this. The frame is something like this. There are two rings. One of them could go into the other. And then you have a sort of screw here which will hold it here firmly. Now what one does is you put your clothes in this and then do the stitching. So then the cloth will remain stretched here and you can do the artwork. Now instead of a cloth, suppose you use a rubber sheet. Okay, stretch it in all directions. Right? So we start with a frame, a stitching frame. Into which a stretch I would put it uniform, means in all directions. Is clamped. Now what one does is this. You mark the boundary. Mark the boundary of your stretched rubber sheet. Okay, so mark the boundary stretched portion. Then of course, then release it and take it out. Okay. Before that, you also mark any two points sheet. Now release the sheet. It would have contracted. Original position. Its original position. So what is the situation that you have? You have the following, namely, this is the stretched position that you have. Okay, and you have 2 points marked on. One, say x1, x2. Now, what would happen to this in the released position? This is the boundary. This is the boundary, the rim, and you would end up with a region of this kind. It would have shrunk inside, and the distance between x1 and x2 would be now visible. And what you would observe is that the distance from x1 to x2 here and the distance from x1 to x2 here, this distance is going to be smaller than this distance. Okay, so let me rework it. So there is essentially, this can be looked upon as a map T from this region to this region, and all these points would go inside this marked region, and you see that this can be considered as Tx1 and T. These are the 2 points. So the distance, we observe that the distance from x1 to x2 is greater than and this is true because I have assumed that is uniformly stretched in all directions, and our assumption that the sheet is uniformly stretched assures that assures that the distances contract. That is satisfying this inequality. So let us mathematically formulate it. You have a map from, this is, suppose I call this x into x. So T is a map from and by the way in which we have assumed to be continuous and a contraction. Contraction. So the question that you ask is, does there exist a fixed point? Is it unique? So there are two questions that you ask here at this stage. That is the first question. Secondly, does there exist a fixed point for T? Is such a point unique? If it exists. Now this is the problem that we are having. Okay. So we try to work out a theorem of this kind. Now let us now define what is called contraction. I think that really sets the problem. We will now formally start working on this. Okay. Up to now, it was not very precise. From now on, we are going to be rather precise. So let contraction definition. Let be metric spaces. So that we can comfortably talk about distances both in the domain and in the range. A map T from Y is said to be contraction if there exists a constant C one. Such that the distance is less than or equal to C times the distance from X to. So T is a map from X to Y, and what it says is this: so you have got dx, dy as the distances. It says that if you take 2 points x1 and x2, and this is the map T, this is Tx and Tx prime, the distance between x and x prime is greater than the distance between Tx and Tx prime, or the distance between Tx and Tx prime is strictly less than the distance between x and x prime. That is what you mean by a contraction map for every x and x prime. That is the what you call the contraction mapping. Now we make some remarks. Some remarks are worth looked into or proved. I leave the proof to you. The first remark is that any contraction is continuous. And hence uniformly continuous. In fact, you need not say that the map is a continuous map. Once it's a contraction, it is not only continuous, it's also uniformly continuous, and that's very easy to do. The second, because of this inequality, it is easy to prove, and the value that C lies between 0 and 1 is a contraction. You say Lipschitz continuous, and this would serve as the Lipschitz constant. Second one, suppose you have an f from a close bounded interval AB into CD differentiable and mod f derivative of x is less than or equal to C, where then f is a contraction. That's an example. It's quite easy to prove because all that you need to prove is the mean value. Okay, that would serve the purpose. right? Use mean value theorem, then straight away follows. The third example, or the third statement that we make is the following, the third remark. Let xy be assume y is a and f is a then what could one say about but this is an exercise that would be possibly worthwhile to do. Okay, now we are in a position to state the fixed point theorem and give a proof of that. So we shall postpone it to our next lecture, possibly tomorrow. Thank you very much.